Welcome back. So next topic for us will be conservation of energy. Number 5. In this class, we call it energy balance. And we start from closed system first. Energy balance for closed system. In other words, it's just conservation of energy for closed system. After that, and we're going to move on to conservation of energy for control volume. Okay, actually, this law has a name. It's the first law of thermodynamics. For closed systems. And what is first law? Just conservation of energy. That is first law. Whenever you hear somebody talk about first law of thermodynamics, you should realize it is just conservation of energy. Okay, so first of all, let's derive this equation. You have a closed system, meaning there's no inlet, no outlet, no mass transfer. And we draw the dashed line indicating everything within the dashed line is my system. Okay, do you remember what the dashed line itself is called? The dashed line itself is called control surface. Okay, so now this is my system. Everything inside the dashed line is my system. Okay, so your system may gain heat. You can think of this as your engine. So first of all, what's going to happen in the engine is you burn the gas. What does burning provide? Burning provides heat. So what's going to happen is Q, meaning heat transfer, goes into your engine. And then what comes out of your engine? Your engine generates work, the movement of the piston, which you can use to drive your car. So mechanical work comes out of your system. Okay, and then we're very close to the equation now. You can think of Q as deposit and W as spending, your system as your bank account balance. So for example, let's say you earn 10 bucks, you deposit 10 bucks into your account, which means Q is equal to 10 bucks. And then you spend 2 bucks, meaning W is equal to 2 bucks coming out of your account. So 10 minus 2, that is 8. What is that 8 bucks? That is the change of your bank account balance. For change, we use delta. And in this case, it's the change of E, which means the change of total energy of your system. Okay, so let's do it again. Q, you can think of it as a deposit. Q equal to 10 bucks. W, you can think of spending, which is equal to 2 bucks. 10 minus 2 is equal to 8 bucks. What is 8 bucks? 8 bucks is the delta E, the change of your balance. Okay, so now can we write this equation now? We deposit 10 bucks. However, you spend 2 bucks, so minus sign, spending. Deposit minus spending. What is that 8 bucks? 8 bucks is the change of your account balance. In this case, delta E, the change of the total energy of your system. All right, so more conventional. So that's it. That's it. That's our first law of thermodynamics for a closed system. Very straightforward, right? Okay, just let's continue. Delta E. Do you remember how many components capital E has? Yes, there are three components in E, capital E, total energy. They are the change of, because delta means change, so delta E has three components. Delta K, the change of kinetic energy. Second component, delta PE, the change of potential energy. And then the last one, delta U. Don't forget delta U, the change of internal energy. Coming to this class, you must realize total energy has three components. They are kinetic energy, potential energy, and internal energy. Internal energy is represented by the temperature of the object. Usually, if the object is at a higher temperature, that means it has more internal energy. Okay, all right, so this is our equation. And our equation, let's just write again. Q minus W equals delta E. And this is our option number one. Option number one. First law for a closed system, option number one. What is our option number two? We can easily rewrite this equation into a different format. How do we do that? It's very straightforward. We just divide every term in this equation by time. So let's do the first one, Q over time. Heat transfer over time, what is that? Q dot heat transfer rate minus W over time. What is W over time? Work over time is power, which we use W dot for. And then the last one, delta E over time. So we can rewrite it to differential E over dt. dE over dt. We can change delta to differential if the step length is really, really small. Okay, all right. And then we can also continue dE over dt. How do we write dE over dt? And then again, we expand capital E into the three components. dKE over dt, dPE over dt, and then the last one, d internal energy over dt. Okay, so you have two options for first law. If you have a closed system, you can choose one that is the best choice for the problem. Okay, to help you understand this first law for a closed system, we're going to do one example right now. Okay, so we have a piston cylinder assembly. This is the piston. And what's inside is the gas. Then I draw the dash line so people know everything inside the dash line is my system. In this case, my system is the gas. Okay, and now what we give you is given mass of the gas is zero point 0.4 kilogram, and PV with the index of 1.5 is equal to constant. So that means the index N is given as 1.5. And then P1, initial volume, initial pressure is given 3 bar. Initial volume V1 is given as 0.1 cubic meter. And the final volume is given as V2, which is 0.2 cubic meter. So volume becomes bigger, which means this is a expansion process. And then we tell you delta lowercase u is equal to negative 55 kilojoule per kilogram. Delta lowercase u. Delta means change. Lowercase u is specific internal energy. So the change of the specific internal energy of my gas is negative 55 kilojoules per kilogram. So that means the internal energy of my gas is going down. And then the problem said you can neglect delta Ke and delta Pe. So you can neglect the change of kinetic energy and the change of the potential energy. Okay, do you think it's reasonable for us to neglect delta Ke and delta Pe? The answer is yes, it is. Why? Because what is delta Ke? Delta Ke is final kinetic energy minus initial kinetic energy. And my system is gas. Okay, so what is V1 for gas? What is the initial velocity for gas? Zero, it's not moving. So this term goes to zero. What about the final velocity, V2? Here, V is velocity, not volume. V2, what is the final velocity of the gas? In the final state, the gas is not moving, so V2 is also equal to zero, which makes the first term go to zero. So delta Ke is equal to zero. It is reasonable for us to say delta Ke is equal to zero. What about delta Pe? Do you think it's reasonable for us to neglect delta Pe? What is delta Pe? Mg delta z. Delta z is the change of height. and this is for gas again. And what is delta Z for gas? What is delta Z for gas? The change of height of the gas is zero. The gas doesn't change height, it's horizontal. It's expanding horizontally, so the height of the gas doesn't change. So delta Z must be equal to zero. That makes delta PE equal to zero. Okay, so it is reasonable for us to say we can neglect delta KE and delta PE. Okay, and so now what we want to do is we want to find out Q, and the unit we want is kilojoule. All right, so we want to look for heat transfer Q, and what equations do we have for a Q? Which equation that we've learned that has Q in it? There's only one, which is first law of thermodynamics for a closed system. Q minus W is equal to delta E. So before you apply this equation, you have to check, is your system a closed system? Because this equation is only for closed systems. So let's see. Our system is a piston cylinder assembly. Do you see an inlet? Do you see an outlet? Do you see mass transfer for your system? No, there's no mass transfer. So yes, my system is a closed system. So yes, I can use this equation. All right, so let's start from first law of thermodynamics. Q minus W equals delta E. And then let's continue. Like we said before, total energy has three components. They are delta KE, delta PE, and delta U, U meaning total energy. And the problem said we can neglect delta KE, neglect delta PE, so those two go to zero. And then in the end, we're looking for heat transfer. So move the one you're looking for, Q, to the left-hand side, and then everything else to the other side. It becomes W plus delta capital U. Okay, so in order for us to find Q, we just need to find W and delta U. As long as we can find those two terms, we can find Q easily. Okay, let's start from the first one, W. W, how do we find work? We can use the equation we derived earlier. P1 V1 N V2 1 minus N minus P1 V1 divided by 1 minus N. That is the equation we used before. And then we just repeat. P1, 3 bar. Make sure you use Pascal. Multiplied by V1 initial volume, 0.1 given. Index N is given 1.5. Multiplied by V2 final volume, zero point 0.2 cubic meter. And index 1 minus 1.5. Minus P1, again, make sure you convert bar to Pascal by multiplying 10 to the fifth. Multiplied by initial volume, zero point 0.1 cubic meter, SI unit already, and divided by 1 minus 1.5. Okay, our solution is 17. 573.59 joules. And then we can convert it to kilojoules, which is 17.6 kilojoules. All right, so now we have the first one in the right-hand side, W, solved. And next one, we look for delta capital U. Delta capital U. Okay, let's recall what is the relation between capital U and lowercase u. The definition of lowercase u is capital U divided by mass. So now we can rewrite capital U into mass times lowercase u. And then, does mass of my system change? Does the mass of my gas change? No, it's a closed system. The mass of my gas doesn't change. So I can take mass out of the delta. So now we have mass times delta lowercase u. Do we have mass of the system, the gas? Yes, we do. Do we have delta u, delta lowercase u? Yes, it's given. So things become really easy. We just plug and chug. Mass is zero point 0.4 kilogram. Multiplied by, what is delta lowercase u? Negative 55. Okay, and this is kilogram. What is the unit for Negative 55. The unit was given as kilojoules per kilogram. So the 2 kilograms will cancel each other. So our solution will be 22. Negative 22. And the unit left is kilojoules. Negative 22 kilojoules. Alright, so now finally we can go back to our equation, which is this one. Q is equal to W plus delta capital U. And now I have both of them. W is equal to 17.6 kilojoules plus delta capital U, which is negative 22 kilojoules. This is kilojoules, this is kilojoules. So my solution is a negative 4.4, also has a unit of kilojoules. So this is my solution. My Q is equal to negative 4.4 kilojoules. And now let's just do one more thing. My solution for Q is equal to negative 4.4 kilojoules, which is a negative solution. What does that mean? Do you remember the sign convention for Q? If Q is equal to positive number, that means your system gains heat. If Q is negative, that means your system loses heat. So for this case, your system, which is the gas, loses heat.